Hello there. Today we'll be doing swimming in the rising water. This is number 143. Wonderful stuff. We're getting to 150 and we'll be repeating all the problems once more. So in swimming in the rising water, what we're trying to do is reach n minus 1 square. So this is the final square is equal to length of grid minus 1. For some reason it's red. That means it's not in the right order. Okay, great. So we start from the 0, 0, and I think we should write this as start and end. I think that's better. So we start from this particular top left square and the bottom right square. As you can see, these are two examples that are given to us. In the first one, it will take 3. We can either go this route or this route. In the second one, we can go all the 4 directions and reach 6 in this particular way. So one thing to note is that we're trying to find a way that reduces the minimum number of items that we can, minimum number of time that takes for us to get there, which is 16. In this particular, 16, right? Yes. So how does this work is that we're going to use Dijkstra's to go using a min heap to do a breadth first search and use the minimum item as our next particular move. This way we go from 0 to 1 and 1 to 2 instead of any of these other directions. But all the other directions are still within play. Being that if suppose we reach some particular direction here that forces us to go to 116, we will end up moving to a different route where we go to 21 instead, and then move down to 15. And so in this way, we always choose the minimum item that is that's available to us. This gives us a time of, because it's a min heap and we're just going through the breadth first search. I mean, the minimum number of items that we're gonna go through is O of n times n, which is here. And when we're pulling out of the min heap, that's a O of 1 time, and when we're inserting into the min heap, we're inserting, it takes log n time to insert. And so if we're inserting all the items, well, that's going to be log n time, but we're not going to insert every single item. And well, yeah, possibly we could be inserting every single item because the list just keeps growing larger and larger. So the runtime is O of n squared times log n, with the space complexity of n times n, because we're storing all the items possibly. Okay, with that, let's get started and let's go create this min heap. So let's start off the min heap. Is going to have a time, a row and a column. So that's going to set us up with a tuple and a grid. We're going to start at the start point. And we're going to start at the starting row and starting time. Perfect. And visited is going to be equal to a set of rows and columns, which is the start and the start. One thing to note, that's good, that's fine. Okay, so direction is that we're going to go to the 4 directions, right? So we're gonna go up, down, and left and right. I wish I could name these, but, well, no, that's a different story. So anyways, while min heap, we're gonna get the tr and c, the time, the row and the column. So we're going to do a heap queue dot heap pop min heap. One thing to note is that if we do this instead, I think it's a little longer, but I think it will help readability into the future. So if row is equal to the end, and the column is equal to the end, then we're going to return time. That means we have reached the end. Otherwise, we're going to keep going into the 4 directions. So it's like a base case, but we are going into a different. We're using a min heap. This does not allow us to run the four items into a variable, into a function. So we have to go through this method. So anyways, let's go take the next row, and the next column is equal to the row plus the direction that we're going to go in, and the column plus the direction column. With that, we have created the next position, and let's check if the position is not inbound, and we can continue. So if next row is less than 0, or next row is greater than the end, or well, let's make this into a multi-row. Next column is less than 0, or next column is greater than the end, or the next row and the next column is already in the visited. Then we will continue. Otherwise, we will insert it into our visited dot add next row and next column, and we need to insert this into our min heap. So heap queue dot heap push min heap, and what we're going to push in is going to be a tuple of a time, row, and column. So for the time, we're going to get the max between the current time and the next time. That tells us the time it takes to get to that particular location. So the current time and the next time would be grid of next row and next column. And once we have that max the time, we are going to add the next row and next column, and we are good to go. And with that, we will pursuit all the way down until we reach the end. Because the end is always existing, we do not need to return a null. Looks like we have a typo here, and I presume this should be good to go. Let's submit it. Okay, it looks good. Pretty nice solution here. I think it is impossible not to have a end, so because it's predefined. So that's the code. I hope that we learned something today. One thing that I would like to add is that how would you even identify the Dijkstra's, and how would you identify that this is the right place and the right time to pull out the min heap? I think that's about like just reading the problem and thinking about the solutions that you've used. So I guess it's about using Dijkstra's many times, and in this particular situation, to just see that particular solution to be the most efficient. Otherwise, I mean, we could travel down each particular route, and that would just take forever. Yeah. n to the n power. Anyways, if you enjoyed this video, like and subscribe. If you want more videos, check the link in the description below. Thank you very much, and I will see you in the next one.